Okay. So last time we talked about Young tableau, and we associated. So Young tableau is a Young diagram together with some number fit. Yeah, so I put one example as well. And then we given a Young tableau. That means the diagram with the number fit. We recall that P lambda is the collection of permutations of Sn, such that these permutations preserve each row, and Q lambda are those permutations which preserve each column. So sigma restricted to 1 to 6 will be a permutation. In this example, sigma restricted to 1 to 6 will be a bijection on this set 1 to 6. And similarly 7 to 11 and 12 to 16 and 13 and 18, or 17 and 18 on the set. And Q lambda preserves each column. So it will send 1, 7, 12, 17 to some permutation of it. Yeah, and similarly 2, 8, 13, 18 to some permutation of it. So in particular, it will fix 6. 6 has to go to itself. So those kind of permutations of Sn, or S18 in this case, will belong to Q lambda. And of course, this forms a subgroup. Yeah, so P lambda and Q lambda are obviously subgroup, because if two permutations preserve row, then their composition will also preserve row. And similarly for columns. And then we defined A lambda as sum of elements of P lambda. Yeah, so we think of it as this A lambda as an element of the group ring C Sn, and B lambda we define it to be plus a sum of elements of Q, but with sign in front of it, sign of sigma. So if sigma is a odd permutation lying in Q, then you put it with negative sign. If it is even permutation, then you put it with positive sign. And then C lambda, we define it to be the product of A lambda and B lambda. Yeah. So one observation note is that P lambda intersection Q lambda is indeed identity. Yeah. So if something fixes all rows and all columns, then of course that tells you that one can so since sigma is in P lambda, one can go to only 2, 3, 4, 5, 6. Yeah, but it's also in Q lambda, so it can go it can't go to 2, 3, 4, 5, 6. It can go only to 7, 12, 13, and 17. But being P lambda, it cannot go to that as well. Yeah. So that tells you that one, and the only possibility for one to go anywhere is 1. And similarly, all the other elements. Yeah. So the intersection of this P lambda and Q lambda is just identity. If it has to fix every column and every row, then it has to fix the cell itself. Yeah. So that tells you that P lambda intersection Q lambda is identity. Okay. So this in particular tells you that if I take some element P and Q, where P is in P lambda and Q is in Q lambda, and some another element P prime and Q prime with the same property, and if their product happens to be same, then P and P prime is same as P is same as P prime and Q is same as Q prime. Yeah? So this is the standard trick in group theory you must have seen. Yeah, because so the reason is you just take multiply by P prime inverse and Q inverse. Yeah. So if you sense so maybe this is the standard trick, since P prime inverse P is equal to Q prime Q inverse belongs to P lambda intersection Q lambda. which is identity. Yeah. So that tells you that P prime inverse P is identity, which is same as saying P is same as P prime. And similarly, Q is Q prime. Okay. So if you think about this this product C lambda, so C lambda is A lambda times B lambda. So you can write it as this. You can do the product. So so you get this formula. But the point is there is no you can't club two elements. Yeah. So it's not like the coefficient of P times Q in C lambda is just sine of Q. Yeah. There is no other other terms. So you can't combine terms. Yeah. So so in C lambda only those elements appear which are those elements of the group appear which can be written as P times Q, and that element has coefficient sine Q. Yeah, there is no other. So if sigma is some permutation of Sn and sigma can't be written as P times Q for some P in P lambda and Q in Q lambda, then its coefficient in C lambda has to be 0. Okay, is this clear? So this is what this means. Yeah. So and each PQ are distinct in the sum. Yeah. So there is no combination. Okay. So that's another way of thinking about it. Okay. So these are some observations. So by the way, so maybe from last time, so before I move into lemmas and stuff, maybe just to recollect. So from last time, we also know that this V lambda, which you define it to be C Sn C lambda, is so we didn't see a proof, but we are heading towards this. So this is an irreducible representation. So this is what we want to representation of Sn. And if lambda is different from lambda prime, two different Young diagram, then you'll get non-isomorphic irreducible representation. Okay. So and then we also saw some things. So some examples we saw last time. So we saw that if we take this the Young diagram is basically an n cycle. So there's only one the partition consists of only one block. Then and then this corresponds to trivial representation. So C lambda happens to be the sum of all elements of Sn. And if it is the vertical one, then we saw that this is alternating representation. Representation. And we also saw some, so for S3, we saw this two-dimensional representation. Yeah, so we did some calculation with some examples. Yeah, and so note that if you replace C lambda by any element of this group ring, then also it's going to be a representation. So this is basically this V lambda is a left ideal. So it's going to be a representation, but with C lambda, it's going to be irreducible, is what we want to show. Okay. So that is the reason we are taking C lambda. Okay, so we'll see some nice property, so some crucial property of C lambda today. Okay, in the group ring. So that's where the fact that it is the group is Sn is going to be used. So today we'll see some crucial lemmas, and then maybe tomorrow next time we will see the proof of this thing. So or I don't know, maybe today. So it's unlikely we will get to the proof of this thing to do itself. Okay. So so first observation note is that a lambda. So remember, a lambda is sum of all elements of p lambda, which is a group. Yeah. So if I take p in p lambda and multiply it with a lambda, what will I get? I'll get back a lambda. Yeah. And similarly, a lambda, if I multiply by p, then I get a post multiply by p, then also I get a lambda. Yeah. Because I mean, it's just so here we are just using the fact that this is a group. Yeah. So maybe I'll write since here. Yeah. So since a lambda is sigma in p lambda. So of course, if I multiply by p, then it's just permuting the sigmas, yeah, which is equal to summation p sigma in p lambda for p in capital P. Yeah, because if you multiply, then it just permutes the order. Left multiplication by a group element is just a permutation of it's just a permutation of elements of the group. Yeah. And this is precisely p times a lambda. Okay, so multiplying by p with a lambda, you get a lambda, no matter which side you multiply. Similarly, if you multiply b by q lambda, so q by b lambda, where q is some element of q lambda, and suppose q is a even permutation, then again it permutes it, and the so remember, b lambda is not just sum, but you have to multiply by sign. Yeah, sign sigma in q lambda. So if you multiply by q, then this becomes so if you multiply by q each of them, q sigma sine sigma, then of course it sigma in q, then this equality doesn't hold, yeah, because you are multiplied by q, but if this will hold only if q has q is an even permutation. Yeah, then sine of sigma and sine of q sigma is same. But if q is not an even permutation, then if it's an odd permutation, then negative of this will go. Yeah. So what you have to do is multiply by sine q. Yeah. If you multiply this by sine q as well, then this is okay. Sine q. Then this identity holds. Okay. Because again, sigma q times sigma is just a permutation of all the sigmas. And now you can just pull out this guy. Yeah, so it's same as sine q times q b lambda. Okay, and similarly on the right hand side. Okay, so multiplying by q p an element of capital P doesn't change a lambda, and multiplying by an element of capital Q changes b lambda by the sign. Yeah, sign of that. That's it. Sign of that permutation. Okay. So here is the first crucial lemma, which we'll note. So for all p in p lambda and q in q lambda, if I multiply this c lambda, pre-multiply this c lambda by p and post-multiply it by q, you get sine of q times c lambda. Yeah, so another way, so I can put sign of q here or the other way, it doesn't matter. Yeah. So this is not this is same difficulty level as the previous one. So this is not bad, but the converse also holds. That is the difficult part. Yeah, so that's where Sn comes in. So moreover, up to scalar multiplication, converse holds. If C is some element in Sn, if C in Sn is such that pre-multiplying P by pre-multiplying C by P and post-multiplying by Q changes C by sign of Q for all P in P lambda and Q in Q lambda, then C must be a scalar multiple of C lambda. So of course, I mean, if you replace C lambda by a scalar multiple, this identity will hold. Yeah. So even if you replace this by scalar multiple, then this identity will hold. Right. So that is the best you can hope. Yeah. So let's see a proof of this this lemma. So this lemma and some. So these lemmas will be helpful. So we want remember we are heading towards this. Yeah. So what we will show is that C lambda is almost an idempotent. So square of C lambda is some number times C lambda, some non-zero number times C lambda. Yeah, so we are heading towards that. But okay. So first of all, to prove this usual direction, note that P times C lambda times Q. So sine of Q times P times C lambda times Q is, so maybe I should have written here the first, so maybe start with sine of Q times P C lambda times Q is this. So you replace C lambda by A lambda times B lambda, but P times A lambda is A lambda and B lambda times Q is sine of Q times B lambda. So the sine of Q square is just 1. So you get A lambda times B lambda, which is C lambda. Yeah. So this is true for all P in P lambda, capital P lambda, and Q in capital P. Right. So this, as I said, is same difficulty as that one. Now let's try to prove the converse. Yeah. So now we take some element in the group ring, and we assume that this property holds. Yeah. So we assume that PCQ times sine of Q is C for all P in P lambda and for all Q in Q lambda. Then we want to show is that C is alpha times C lambda for some alpha in C, for some alpha complex number. Yeah. So now note that C, if I so this condition tells us that C is same as so I'm just multiplying it by P in P lambda and Q in Q lambda. Yeah. So and then sine of Q. Yeah. So I get C. So I'm just using this identity. And say C, so C is going to be is a linear combination of G. Yeah. So NGs are so NGs are some complex numbers. Yeah. So that is how C belongs to CSN, means it looks like this. Yeah. So now C is so if we use this identity, that tells you that C is sine of Q NG times PGQ. Yeah. So you are P multiplying by P and then post multiplying by Q. So you get this. Right. but the coefficient of PGQ in C is n sub PGQ. Yeah, so that tells you that n sub PGQ is same as sine of Q times NG. Okay. So from this this thing which I have boxed, we get this identity. Yeah, that NG. So maybe I'll erase this box now. Okay, so we get this identity that NPGQ is sine of Q times NG. Okay, so by the way, we want to show that C is a multiple of C lambda. Yeah, and we know how C lambda looks like. So we have this description. C lambda is this kind of guy. So we want to show is that if G is an element of if G is G in Sn is such that it can't be written as P times Q, then we want to show that n sub G is 0. Yeah, and for the remaining, we want to show that it's it is a multiple of one of the guys. Yeah, so maybe it's a multiple of. So what is the coefficient of? So identity appears here. So note that. This is going to be so coefficient of identity. Identity is identity times identity. So it's E plus something. So it's either plus or minus 1. So E will come with coefficient 1. Yeah. So I have to show that the coefficient of NE in C is yeah, so coefficient of PQ in C is and coefficient of NE in C are plus or minus 1 of each other. Yeah, so they are sort of multiples. So they only differ by Q, sine of Q. So that is where we are heading. Yeah. So if NPGQ is sine of Q times NG, then that tells you that NPQ is sine of Q times NE. Yeah. So that tells you that if we prove that PQ is basically NE up to sine of Q. So this is what we wanted to say about the coefficient of C in coefficient of PQ in C. Yeah. But the second part is to show that if G is not of the form PQ, then we want to say that NG must be 0. So NP also C lambda is of this form. So we are almost done, except that we want to show that NG is 0 if G is not equal to PQ. G in Sn, if G is some element in Sn such that it's not equal to PQ, then we want to show that NG is 0 for any P in P lambda and Q. Yeah. So far it's okay. Yeah, makes sense.
Yes, sir.
Yeah. So we will. So now we will show that NG is indeed 0. Yeah. So first we consider this tableau, another tableau which will be useful. Yeah. So let lambda prime be another tableau called G times lambda. Okay. So what we do is we just permute the entries of. So if lambda is something like this, yeah. So we just permute the entries of this by G. Okay. So one I'll replace it by G1. 2 I'll replace it by G2 and so on. G is a permutation of these n numbers. Yeah? So that is how you get lambda prime. Yeah? Be the tableau obtained from lambda by replacing I in lambda by Gi. Okay, that is what we are doing for I between 1 and n. Okay, so that is how we obtain lambda prime from lambda. Okay. So the claim is if G is not in PQ, then there exists a pair of integers between 1 and n, such that this pair appear in the same row of lambda and in same column of lambda prime. Okay. So there are two integers. I don't know. I don't want to give them a name, but if you like, x and y, two integers between two distinct integers between 1 and n, such that x and y lie in the same row of lambda and same column of lambda prime. Okay, so if so this claim we will prove, but assuming the claim, we will show that if this claim holds, then we will show that that ng is indeed 0 if g is not of the form pq. Okay. So assuming the claim, let t be that be the transposition of these two integers. Okay. So you had these two integers x and y, and so you consider the t as the transposition of these two integers. Yeah. Then of course t belongs to p lambda, right? Because it what this t does is just interchanges these two. Yeah. So all the rows are of course fixed except for one particular row where all the entries of every row is fixed except for one particular row, and in that particular row also this only two elements are interchanged, so it preserves rows of lambda. Yeah. So t of course belongs to p lambda, and similarly t also fixes all columns of lambda prime. In fact, it fixes almost everything. It only changes two guys. Yeah. So and they happen to be in same column of lambda prime. So t also belongs to q lambda prime, the new tableau which we have constructed. Okay. So, but what does t belonging to q lambda prime means? It means that G inverse TG, yeah. So G inverse TG, what does it do? This is also a transposition, yeah. And what does this transposition do? So you can see, you can check that this just changes GI and GX and GY, yeah. So it will. So this will fix all the columns of q lambda. Okay, this transposition. So one way of thinking about it is if you take a column which does not contain x, if it does not contain gx or gy. Okay, so most of the entries are fixed by this, yeah, because you apply g and then you t fix if gx is not so you take some I, and if gi is not x or gi is not y, then t will not do anything, and then you apply g inverse, so you get back I. So the only thing it will change is if I happens to yeah, so if GI is X or GI is Y, then it will interchange so and GJ is Y, then this will interchange I and J. Yeah, that is what it will do on this one. So of course, if x and y are in the same column of q lambda prime, that tells you that, but q lambda prime was made by making this change. Yeah, so that tells you that I and j will be in the same column of q lambda. Yeah, so that tells you that this guy actually lies in the same this G inverse TG is in q lambda. So then G inverse TG is just this transposition. is the transposition ij. Maybe so since I've used xy, maybe pair of integers xy such that they appear in the same row of lambda and in the same column of lambda prime. Okay. So T is just xy. T is the transposition xy. It interchanges x and y. So is this clear so far? Yeah. So now, so we have got a transposition T, which is in P lambda, and this. So we want to. And G is some element which is not in PQ. So and we have got that G inverse TG is in Q lambda. Yeah. So so what does that tell us? So we will use this identity again. Where did it go? And this identity again. Yeah. So that tells us that n. So this is in P. This is in. So this is in P lambda. I meant. And this is in Q lambda. And so we multiply something by an element in P lambda, something by Q lambda. Then what we change it by sign of the element in Q lambda. But this is again a transposition, so the sign is negative. So n sub this is same as minus ng, but this guy G inverse, but this is same as ng. Because G inverse gets cancelled and T square is identity, and what remains is G. Okay, so we get Ng is same as minus Ng, which implies Ng. Okay, so assuming the claim, we are done. Yeah, so hence C is going to be some constant times C, and that constant is any. Yeah, so it is any. C is any times C lambda. Okay, so far so good. Yeah, so all we have to do is prove that if G does not belong to PQ, then there exists a pair of integer xy such that they appear in the same row of lambda and the same column of lambda prime, where lambda prime was this tableau we obtained by modifying the entries of lambda by G, the permutation G of S. Okay, so let's any questions so far? So this is the tricky part of the proof. So that's why I'm trying to go a little slow. Yeah, it's not really as conceptual. It's just some computation. Yeah. So this is where all the hard work goes in. So meaning, of course, some hard work is in trying to do things, understand things conceptually, but sometimes, but at the end one has to do some computation, and this is the computation part of this work. Yeah, Young's work. So let's prove the claim. So what we'll show is that if no such pair of integers exist, yeah, so that means if so there are no two integers which lie in one particular row of lambda and in one particular column of lambda prime, then we will show that G happens to be in PQ. Yeah, so that will prove the contrapositive. So suppose no such pair of integers exist, then we want to show that G is indeed in PQ. Okay, so let's try to understand what this means. Yeah, So say lambda, so maybe I'll use this example. So no such pair exists means if say lambda is 1, 2, 3, 4, 5, 6. So first row of lambda looks like 1, 2, 3, 4, 5, 6. Okay. So so suppose no two elements of lambda. So no two elements of this particular row is in same column of lambda prime. What will that mean? That will tell us that these numbers 1, 2, 3, 4, 5, 6, they appear in different columns of lambda prime. Yeah, because if they happen to be in the same column, then that will contradict our hypothesis. So that tells you that 1, 2, 3, 4, 5, 6 appear in different columns of lambda. Okay. So if I permute this 1, 2, 3, 4, 5, 6, so say I appear in jith column of jith column, then I can look at this permutation which sends I to ji. Yeah. So I don't know why there is an S here. Gi. So say I appear in the jith column. So this is this. So I mean, so we are looking at the first row, which has the maximum number of columns. Yeah. Which is the longest one. Yeah? So this I going to gi is a permutation of these 1 to 6. Yeah. So P1. So P1 which sends I to ji is a permutation which and it fixes the first row of lambda. Yeah, and it doesn't do anything to the other rows. Yeah, in fact it preserves the first row of lambda, and in fact it fixes every other entry. Yeah? So this P1 is actually in P lambda. Okay. And if I consider the tableau P1 times lambda, yeah, that means I'll just permute these 1, 2, 3, 4, 5, 6. One will go into J1 column of the first row instead of first column. 2 will go into J2 column, and so on. And then what happens is in P1 lambda, I will appear in the jith column of the first row. Yeah. So this is what is happening. Yeah. So then you so I've made sure that I have permuted this such that these 1, 2, 3, 4, 5, 6 appear in the jith column of lambda of P1 lambda. Yeah? And in lambda prime also they appear in the jith column, but not necessarily in the first row. Yeah, some other row. Okay. So what now in of course there exists. So if I interchange the first entry in the first row with, of lambda prime and I, the I and I appears in jith row, jith column, and something appears in the first row, yeah, of the jith column. So if I switch them, then I'll the first row will become same. Yeah. So let Qi be the permutation which switches one jith entry of lambda prime. So one jith meaning the first row and jith column, and I. And I remember is in the jith column, but not necessarily in the first row. Yeah. So let Q1 prime be the product of these transposition. Yeah. Then of course this Q1 prime it fixes all the columns of it. It preserves all the columns of lambda prime. Yeah, because we are doing transpositions in a particular column. Yeah. So this Q1 prime fixes each of the preserves each of the column of lambda prime. So that tells you that Q1 prime is in Q lambda prime. Okay. Yeah, so what was lambda? Lambda prime was G lambda. Yeah, lambda prime was G lambda. Okay. But by what I had explained, this is Q lambda prime is same as G Q lambda G inverse. Okay, so it's the same logic which I gave you here. Yeah. If T belongs to Q lambda prime, then T is in G Q lambda G inverse. Okay. So that tells you that Q lambda prime is just G Q lambda G inverse. So Q1 prime belongs to this guy. And so now if you look at these two tableaus, P1 lambda, so P1 lambda had entries 1, 2, 3, 4, 5, 6, but they were rearranged to ensure that 1 is in J1 column, 2 is in J2 column, and so on. And if you consider Q1 prime, lambda prime, they're both of them has same first row. Yeah. So we first ensured that all these go in the right column, and then we for lambda. So that's how we obtain P1 lambda. And Q prime lambda, we made sure that these 1, 2, 3, 4, 5, 6, wherever they are, they come in the first row. Yeah. So P1 lambda and Q1 prime lambda prime, their first row are identical. Does this make sense, guys? Yeah. So 1/1th entry of P1 lambda is just so what is it? So 1/1th entry, I don't know. 1/ith entry is GI. Sorry, no. Is GI? Yeah. So it's the inverse permutation. But I hope this is clear. Yeah. The first row of P1 lambda and Q1 prime lambda prime, they are identical. Yeah. So what we did was P1 lambda just permuted these 1, 2, 3, 4, 5, 6, so that 1 goes into J1, 2 goes into J2, and so on. And so they are in the same column of lambda prime, and then we made sure where I appears. Yeah. So 1 comma Ji contains I. Yeah. So 1 comma Gi entry of so I can tell you what the value is. Yeah, are identical. So in fact 1 comma Gi entry is I in both P1 lambda and Q1 prime lambda prime by the permutations we have chosen. The way we have chosen P1 and Q1 prime, this will happen. Yeah. So the first row is identical. Okay. So now we can repeat this with the second row as well. Yeah. So we'll get some with this. So we'll replace lambda by P1 lambda and lambda prime by Q1 prime lambda, and apply this to second row, and so on. So if we do it for all the rows in lambda. So lambda is lambda and lambda prime are the Young diagram is same, just the entries are different. Yeah. So if you run through all the rows, what we can ensure is that after these changes, we will get that they become same. Yeah. So so what we can ensure is that there is a p in p lambda. So if you you will have to pre-multiply by p2 and p3 and so on. So their product is again in p because each of these pi's are in p. Yeah. So we can find a p in p lambda such that p times lambda is equal to q prime times lambda prime, where q prime is in this q lambda prime. Yeah. So here again, you instead of q1 prime, you'll get some q2 prime and so on, but q2 prime, q3 prime and so on, product of these things if you do it for a second row, third row and so on. But the product is again in q lambda prime. Okay. So p lambda is same as q prime lambda prime as Young tableau. Yeah, so that tells you that I mean it's a Young diagram. So the permutation. So that but lambda prime was g lambda. So if you replace it by that, so that tells you that p and q prime times g, they are the same permutation. Yeah? So p changes the entry of lambda, and q prime g changes the entry of lambda as well. So by q prime g permutation, and p changes by p permutation, and they end up in the same guy. That tells you that p is same as q prime g. Okay. So and of course q prime, remember, is in q lambda prime, which is g q lambda g inverse. Yeah. So q prime, we can write it as g q g inverse for some q in little q in capital. Yeah. So now you apply these two facts. So p is q prime g, but q prime we will write it as g q g inverse. So we get p. So this g inverse cancels out, and what we get is g is p q inverse. Yeah, which of course belongs to p times q. Right. So we have proved the contrapositive. We wanted to show that G belongs to P times Q, and that's what we have done, assuming that no such pair exists. Is this okay? So as I said, the proof is somewhat tricky, but meaning it's somewhat computational. But I hope I've made it clear enough. Yeah. So what's the consequence of this guy? So as I said, we'll prove that this implies C lambda is almost an idempotent. Yeah. So in fact, the corollary is that for any element x in the group ring, C lambda x C lambda is alpha times C lambda for some alpha in C. In particular, C lambda square is n lambda times C lambda for some n lambda in C. And later on, we will see that in fact n lambda we can also ensure that n lambda is non-zero, or maybe later. But this is just immediate from this lemma. Okay, so we want to show that this guy is some scalar times C lambda. So we will just show that this satisfies the hypothesis of this lemma. Yeah, so we want to show that P times C lambda x C lambda q times sine of q is C lambda x C lambda. Yeah, then it will follow from that lemma. So let C be C lambda x C lambda. We want to show is scalar multiple of C lambda. Then let's just look at PCQ. Yeah. So PCQ is P C lambda x C lambda q. Yeah. But C lambda is A lambda B lambda. So we expand all that as well. Now P A lambda is A lambda. So nothing changes. And then we have B lambda x. A lambda, and B lambda times Q is sine of Q times B lambda. So that sine of Q comes here, and we have B lambda. Yeah, and then sine of Q, and then this guy, of course, this is C lambda x C lambda, sine of Q times, which is to say this is sine of Q times C. Okay. So this is true for all P in P lambda and Q in Q lambda. Okay. So we have this. So hence by our lemma, C must be a scalar multiple of this for some alpha in C. Yeah. So it follows directly from the lemma. Okay. So yeah, so there's another lemma, and yeah, so I don't know. Yeah, so maybe we can finish this as well. Maybe we'll do this next time. Yeah. So there are 3 minutes left. So yeah. So maybe I'll just tell you what the ordering is and state the lemma, and maybe next time we'll see a proof. Yeah. So let lambda and mu be 2 Young diagram. We can order any 2 Young diagram via this method. Yeah. So lexicographic ordering. Yeah. So like Young diagram means it's a partition. Yeah. Lambda 1, lambda 2, lambda 3 up to lambda k. So that summation lambda is n. Yeah. And mu is similar. So we say that lambda is bigger than mu if either lambda 1, the first row of lambda is longer than the first row of mu, or if they have the same row, you go to the next row and check whether the next row of lambda is bigger or not, and so on. You keep on doing that. Yeah, so that's lexicographic ordering. So another way of saying this is that lambda I minus mu I. The first, so you for I between 1 and k, or whatever number it goes to. So the first entry should be so the first non-zero entry should be positive, and then you say that lambda is greater than mu. Is positive. Yeah. So so that's ordering on a Young diagram. So the second lemma says that if so, what we proved is that in this lemma we proved that C lambda x C lambda is some scalar times C lambda. So this will allow us to prove that V lambdas are irreducible. And then the next thing we'll prove is that if lambda is greater than mu, then A lambda x B mu is 0. Okay. So in particular, this will tell us that C lambda x C mu is 0, because C lambda is A lambda times B lambda. So so this is just A lambda B lambda x A mu B mu. So it's still of this form. Yeah. So so this lemma will help us say that if lambda and mu are different Young diagram, then the representations we get are different. Yeah, so they are not isomorphic representation. Okay, so that then will complete the whole picture. Yeah. So maybe we will not. I mean, the proof is somewhat. So again, it's somewhat similar. So I'll. Yeah. So let's. It's already time. So maybe we'll do this next time. Okay. So we'll finish this lemma, and then So on Monday, we'll complete the proof of this categorization. So the main theorem I have stated here. So that lemma is the other crucial lemma, and these two together is good enough, yeah. And then we will that will help us prove that V lambdas are irreducible, and these are all the irreducible representations. Okay. Maybe it's a good place to stop.